Now that we've learned all about Fourier transforms and how to use them for filtering image frequencies, we're in a position to ask some very interesting questions, including probing the behavior of convolutional neural networks. The central question we're trying to answer is, do CNNs primarily rely on low or mid or high image frequencies for classifying images? And this is a question that you'll answer for yourself in the final project. First, I'm going to show you a preview of what result you're expected to get in the final project. This is the image data set that you will work with. It's Fashion MNIST. The images are small, grayscale images that are fairly simple. They're on a black background and they're all labeled. You will build a convolutional neural network that doesn't have to be particularly complex. For this simple data set, you just need a couple of convolutional layers and a couple of fully connected layers. And then you will train and test that model on the test set, and you will end up with a test accuracy of just under 80%, just under 0.8. And the next step is you will do frequency ablation, which means that you will create three filters: a low-pass filter, a high-pass filter, and a band-stop filter. A band-stop filter is the opposite of a band-pass filter. It suppresses frequencies in a certain range between a low and a high rather than passing them through. And you will end up with this plot. This is called a CNN frequency reliance curve. And the blue here represents the low pass filter, the orange the high pass filter, and the green the band pass filter. Really, the blue tells the story of the entire plot. So let's focus on that. This data point here is at a cutoff of 15%. What that means is that this low pass filter passed at this point all of the frequencies between 0 and 15% of maximum and suppressed everything else. And you will see that just by allowing the 15% of the lowest frequencies to pass through, the network was able to achieve its maximum accuracy of just under 80%. The orange says precisely the opposite. The orange curve is basically a mirror image of the blue curve. It says that if you suppress the frequencies between 0 and 15%, and allow everything above 15% to pass, that's no good. You will end up with a very low accuracy. Now let's try to interpret what the band stop curve says. Let's look at this point. This is the lowest point in the band stop curve. The way we have coded this, and you will see this in a future lesson, is that we get the cutoff frequency and we compute half of the cutoff frequency. So in this case, the cutoff frequency is 15%. Half of it is about 7%. And we suppress all the frequencies between 7 and 15%. And you can see by doing so, we degrade our accuracy. And that makes sense because 7 to 15% is decidedly within our low frequency range. So if we are suppressing those critical low frequencies, we're expected to get a degradation in our accuracy. This basically says the same thing as the other two curves. If we suppress everything from 0 to 15% instead of 7 to 15%, we end up with an even lower accuracy. And if we allow everything between 0 and 15% to pass, we end up with our maximum accuracy. So in conclusion, with this data set that uses simple grayscale images on a black background, the CNN only needs the lowest 15% of frequencies to make accurate predictions. And if we remove the mid frequencies and high frequencies, that does not affect accuracy. And you will again code this for yourself in the final project. Now I did the same thing with a different data set, Cipher 10. And here the images are a little bit larger, they're in color, they have more texture, a little more detail, and most importantly they have background as opposed to the black background over here. So even though we're supposed to classify a horse here, in the background there's other things. There's people, there's an audience, there's a wall, there's a ground, same with all the other images. So we need a more complex and a larger CNN, as you will see. I'll show you in the future lesson, to deal with this data set. But then we do the exact same thing. We create low pass, high pass, and band stop filters. We apply them after we have trained the data set. We apply them to the images and we test on the filtered images, and we will end up with this frequency reliance curve. And this is a little different before. Here, let's again look at the low pass filter, which is the blue curve. You will see that if we just pass the 30% of the lowest frequencies, we still have a pretty poor accuracy. But if we pass the 30% of the lowest frequencies, and also the mid-range, the 30 to 60% or so, then we end up with near our maximum accuracy. Beyond that, adding the high frequencies doesn't help us. So this tells us that with this particular data set, we rely on low and mid-frequency image features, and we still don't need the high-frequency features. The orange, again, is the mirror image of the blue with the high pass filter and says the same thing. And let's look at our band pass filter here, or band stop filter. Again, let's look at this point. This is the lowest point in this curve at a frequency of 70%. Again, remember how we construct our band stop filter. We say we have 70 here, we compute half of it, that's 35%. We suppress all the frequencies between 35 and 70%. That's all the mid-range frequencies, and we end up with degradation in our accuracy. So again, the green curve says the same thing as the blue curve. It says that we do need the mid-range frequencies for accurate prediction in this particular data set. So, and by the way, I did this was with the ideal filter. I also did it with Butterworth filters that you've heard about in previous lectures. The curves are almost identical, as you might expect with the Butterworth filter. We had a smoother dip in the band stop filter than with it here, but essentially it conveys the same information. So for the purpose of your final project, you can just implement the ideal filters, which are simpler to implement. So in conclusion, with this data set of more complex color images on a non-zero background, the CNN needed the low and the mid frequencies, 0 to 70% of max to make accurate predictions. And we did see that removing the mid frequencies between 35 and 70% did modestly lower the accuracy, but removing high frequencies did not affect accuracy. What we have found here basically replicates what the literature says. This is a paper by Yin et al., 4-year perspectives on model robustness. And they analyzed CNNs directly in the Fourier domain and discovered that CNNs disproportionately rely on low and mid-range frequencies. Let's look at this image. Let's look at the blue curve. This is a low-pass filter of different filter size. So the most restrictive filters that allow just a few low frequencies to pass through are over here. And as we increase the filter size, we allow more and more of the lower frequencies to get through. By the time we get to a filter size of 50 or 40, we're basically allowing enough of the low frequencies to get through to reach model accuracy near its maximum. Again, indicating that low frequencies are the most important for CNN prediction. This is a different paper by Wang, and it was really aimed to talk about the role of high frequency components, and you can read it, but it has a very important plot, which I've shown here, that basically tells us that during training, CNNs gradually shift from high frequency sensitivity early in the training, in the early epochs, to stronger reliance on lower and mid frequencies later on in the training. On this image, the different curves represent different low pass filters of different radii, and we'll talk about what the radius of a low pass filter represents in the next lecture. But basically, with the most, this is a radius of 4, 8, 12, and 18, with very restrictive low pass filters. You don't get very good accuracy no matter how much you train your model. But once you get to a reasonable size low pass filter of, let's say, size 12, that allows a sufficient number of sufficient amount of low frequency components to get through, then as you train, you get higher and higher accuracies. Here we see with this purple curve that initially with this low pass filter, we don't get very good accuracy, which means that in the initial epochs of training, the model really requires the high frequency features of the image. But as we progress through the training to the later epochs, we see that with just a low pass filter of a reasonable size, we can get near maximum accuracy. The gray line here that you can barely see represents the image without any low pass filters, and you can see that with a frequency with a radius of 12 we can approximate that, and with a radius of 16 we're pretty much right on with our maximum accuracy. This recapitulates how human visual perception works. CNNs in many ways are similar to human vision, including structurally, but this is yet another level of evidence here. We know that human visual perception is more sensitive to low image frequencies because we use that very fact in image compression. We carefully preserve low spatial frequencies, coarsely quantize high spatial frequencies, and as a result, we're able to achieve large compression gains with minimal perceptual loss. And it's very interesting that CNNs recapitulate human visual perception in that way. So in the next lesson, we'll go over how to use PyTorch to build and train and test the model, and then how to use PyTorch's fast Fourier transforms to do frequency ablation and come up with these curves that I showed you.